plans for post-Lawrence are to enroll in graduate school, and so she's looking at some master's programs to prepare to go through that. But she's going to talk to us today about sort of melding her interest in dentistry with her experience and understanding in organic chemistry and synthetic organic chemistry. And so some of these things, you might see some big molecules on the screen, so please feel free to pepper her with questions about sort of what these things mean and why they're important. Because I think that this is an important, again, goal in our teaching is that we can explain these things that look very difficult. So unfortunately, I'll have to leave now to run my lab. But before Louis, welcome, Tianyi.
Okay, so first of all, thanks so much for coming. Okay, so today I'm going to talk about mercury fillings and its experimental dental resin replacement. The reason why I chose this topic is because seeing dentists used to be the worst thing in my life. I used to have like a great dental phobia. Like every time when I went to dentist, it was like a looming storm. So, but it also triggers my curiosity toward knowing more about dentistry. So that's why I picked this topic. And I'm going to talk a little bit about organic chemistry and microbiology. So first of all, I want to introduce the structure of a tooth. So on the top is the enamel, which is the hardest tissue in our body, and then below it is the dentin, which is a little bit softer. And under dentin is pulp. So pulp is where the nerve and blood vessel locates. And here is a big cavity under X-ray. And actually this cavity is pretty serious. We can see that it goes to the pulp already. If they don't do anything about it, it will cause serious infection. And then dental caries are among one of the most prevalent oral infectious disease among both children and adults. This just shows a picture of dental caries. So what is the cavity formation process? So first of all, so no matter how much time we brush our teeth, there's always bacteria accumulates in our mouth. And once the bacteria accumulates, it's gonna form a sticky biofilm. So what's biofilm? Basically, it's just a accumulation of bacteria, and it forms a layer. We call it plaque. If we don't do anything to the plaque would interact with the sugar from food, and it would produce acid. The acid would cause the loss of calcium and phosphate and other minerals, which is the first step of dental cavity. We call it demineralization. If we don't do anything to demineralization, it progresses to cavity eventually. So once we have a cavity, we want to get it filled. We don't want it to getting serious. So what's the properties of a dental filling material? So wear resistance, of course, we want to avoid the abrasion caused by chewing force as much as possible. Biocompatibility, we don't want anything that's irritating to the gum tissue or our tongue, and we don't want anything that's toxic. Low cost, yes, at least we want most people to afford it, although it's still pretty expensive. Depends on the surface and the tooth. It's going to cost around $150 to $250 per tooth. Strength, durability, yes, we don't want to replace the fillings each year. We want it to last as long as possible. So mercury filling was the first type of dental fillings. It was first introduced in France and England in 1826. And then 4 years later, it was introduced to the United States. So for most mercury fillings, 50% of them is mercury, and the other 50s are other alloys, but most of them are silver. But there's safety concerns over the use of mercury fillings since it's introduced, specifically neurological diseases. So who's this guy? He's a German inorganic chemist. He is the first one who described symptoms potentially associated with mercury poisoning and then wrote a report about it. That's what I extracted from the report. So he had several mercury fillings since his youth, but with time he started to have symptoms including mild drowsiness, headache, and worsened memories. And it really retarded his ability to work because he has a leg and he is like principal investigator or something at that time, anyway. And then he and another physician finally identified the source of his illness is mercury. But at that time, only light poisoning was much more researched. But after he knew about his the source of his illness, he renovated the ventilation system of his lab because some of the mercury are from the occupation, from the lab. And then he replaced the amalgam fillings. Until now, people are still curious about the potential relationship between neurological disease and the use of dental amalgam fillings. Actually, this research was published last year in December, so it was pretty new. It investigated the potential relationship between Parkinson's disease and the dental amalgam fillings. So people of age 55 to 74 were recruited. So basically like old people. Not too old though. No. They're not too old. Pretty young. In total, 20 and 740 people were included, but they excluded people who already had like dementia or head injury, so as to make sure that all of the patients included in these studies are new found cases. And then they allow a 7 years observation period. During this period, people were divided into amalgam filling and non-amalgam filling groups. After some really complicated statistical analysis, I want to show like the most important findings. So of course, the people with amalgam fillings have a higher hazard rate of having Parkinson's disease than those without mercury fillings. And of course, age-wise, like people of age 65 to 74 have a higher risk of having Parkinson's disease than those 55 to 64 group. So what's the potential mechanism for the association between neurological disease and the mercury poisoning? So no, there's not too much details about it, but that's the one that the paper proposed. So we get elementary mercury from the dental fillings, and then the mercury filling gets converted to methyl mercury by interacting with sodium chloride or acid from food. And then this methyl mercury has higher entry rate across blood-brain barrier. And once we have a lot of methyl mercury accumulated in the brain, it's going to cause oxidative stress in the central nervous system. Actually, we don't want oxidative stress anywhere in our body. Basically, just free radicals that cause damage of like DNA or tissues. But what's finally causes neurological disease is dopamine or glutamate-related apoptosis. So dopamine is a neurotransmitter, and glutamate is also an excitatory amino acid neurotransmitter. So when there's something wrong with neurotransmitter, it must be really bad for the nervous system. And now, but we have a better choice, at least aesthetic-wise, because we really don't want anything that's silver-looking on our, like, especially front tooth. So now we have dental composite resin fillings. It's very close to the, it really looks like the natural teeth. And it was way younger. It was introduced 50 years ago. And it has more applications other than just restoration, although I mainly talk about restoration. And it is still one of the most popular filling materials, at least aesthetic-wise. So these three are the main components of resin-based fillings. So first of all, inorganic fillers. So it's basically silica glass. And this just shows a picture of it. These particles, the size of them ranges from, I think, hundreds of nanometers. And this picture is under SEM, scanning electron microscope. Organic matrix, that just shows an example of organic matrix, and I'm gonna elaborate on it later. coupling reagent. So coupling reagent is basically what cross-link these two stuff together, and also the polymer chain. So that's what happened. Like that's a polymer chain, and that's another one, and that shows the cross-link. Here I want to introduce the concept of radiopaque. So what's radiopaque is that we want to, under X-ray, we want the fielding material to be distinguishable from the rest of the tooth material. That's what radiopaque means. And the properties of the inorganic fielder is really important for this. Really important for this property. And the organic matrix. So what I just showed is just an organic monomer, and we are gonna do a polymerization reaction to make a polymer chain with the monomers. Base GMA and UDMA are the two major types of organic matrix. Let's look at base GMA. So methyl methacrylate. The reason why I point out this group is that that's the group we always want to keep it, because that's where the polymerization reaction starts. Because radicals always attack double bond first. So no matter how much we modify this group, we always keep this functional group. But this one has a con, which is low conversion rate. So only 50 to 60% of monomers get converted to polymers. And it has high viscosity, which is mainly due to the hydrogen bond forming between this COO group and the hydroxy group. That just shows another variant of methyl methacrylate compounds. Well, we can see that we still keep this group, and but we make modifications in here. There's also hydrogen bond forming in here. It's between this amino group and this COO2, but it's way weaker than the previous one. So what's polymerization reaction? So first we have an initiator, and the light, the blue light that I showed in the previous picture, is what initiate the reaction. So the initiator would attack this double bond, like what I said, and then leave a radical. So radical is basically unpaired valence electrons. And then this radical continues to propagate to another molecule like that. And that's what we ended up getting. And as the chain continues to propagate, we get something like that. Actually, there will be millions of it, but I'm just drawing like only 4 of them. Although that composite resin fillings are better choices, but there are still clinical issues associated with it. The first of all is the bacterial adherence. So there's research showing that there are more bacterial adherence on the surface, on the tooth surface with composite resin fillings than that of amalgam fillings. And like what I talked before, the accumulation of bacteria would cause early plaque, and the plaque would cause probably recurrent decay if we don't do anything with it, if we don't care about dental hygiene, and we really don't want recurrent decay. So what we are going to do is that we modify the organic monomers with some antibacterial agent. So a research group in Germany was trying to incorporate an antimicrobial agent to this methyl methacrylate group, so which is the group that we don't want to get rid of, because that's where the polymerization reaction happens. They are called ERGA. That's just a trade name, but basically it's a broad spectrum antimicrobial agent. And here, they do esterification reaction with the ERGA group and methyl methacrylate. And that's what we ended up getting. And they call it methylpryl ERGA. And another thing they modified is polyerga. So what's polyerga? So instead of doing a covalent bond between these two groups, they use these polypore hollow beads. So basically, this hollow beads is still made up of methyl micrylate, but it acts as a absorber, which means that once we load the erga with these beads, the erga is gonna be absorbed onto the surface of these polypore beads. So instead of a covalent bond, they just physically attach these two things together. So experimental setup. So what they do is that they make this material into like really small disc, and then they immerse these materials into real human saliva and bacteria. So what they do here is that they, for material A, they replace part of the inorganic gas fillers with polyerga, which is the thing with the beads. And then B and C, they keep the same, and ST is just a control group. And for B and C, they keep the same amount of inorganic gas fillers. And then they modified part of the organic matrix with methylcryl erga, which is this thing. And then they want to test the antibacterial properties of these 1, 2, 3, these four materials. And here we can see the component of matrix, UDMA and base GMA, which are the two stuff that I just introduced before. That just shows the weight percentage. And these numbers are all by weight percentage. So what bacteria they investigated? They mainly investigated Actinomyces mutans. So these two are both gram-positive bacteria. They all have high numbers in our cavity, and all shows to be related to periodontal diseases. And then here are more, just other gram-positive bacteria. So what's gram-positive bacteria? So there's gram-positive and gram-negative bacteria, and they differ each other in their cytoplasmic membrane. So that's the cytoplasmic membrane of gram-positive bacteria, and that's the cytoplasmic membrane of gram-negative bacteria. So for gram-positive bacteria, we can say there's a thick, sorry, the character is too small, a thick peptidoglycan. So what's peptidoglycan? So based on the word peptido, pep is amino acids, and glycan are sugar. So basically just something like a net cross-linked with sugar and amino acids, which is what's in here. But for gram-negative bacteria, they don't have this thick peptidoglycan layer. They only have a, I think like if you have basic biology knowledge, they only have a very thin lipid bilayer. So that's how they differ with each other. And for this experiment, they only tested gram-positive bacteria because most of our bacteria in our mouth are all gram-positive. And the reason why, I think probably it's probably due to the cell communication pathway. So once like a cell colonizes onto surface, they just send chemical signals to other bacteria, and maybe gram-positive bacteria is better at it, and then they just attract other bacteria, other gram-positive bacteria. So let's look at their results. So their results is very complicated. I only extracted part of it that I think is important. First of all, let's look at these three data from material A, B, and C. So just to remind you guys, TOT is the total number of bacteria. So they just count the bacteria. Each number here represents itself multiplies by 10 to the 6. So it's not just 2.1 bacteria. So it's like millions of them. And VAT is vital. Vital means living cells, and non-vital is dead cells. So let's look at these three data. And we can see that there are more, it seems that there are more living cells on material A than B and C. So which means that B and C have better antibacterial properties than A. And I also point out this data is because, although we see, for A, we see compared to B and C, we see more living cells, but that's the total number. We see more. The total number for A is also more than that of B and C. So which means that although there are more dead cells from here, but the antimicrobial effects doesn't diminish the bacterial adhesive forces, which means that although the bacteria died, but it still attaches to the surface of the tooth. That's what I got from here. Let's take a look at the individual species. So for this one, it's the asthmatis. I'm looking at asthmatis. And then, in order to visually see the dead and living cells, they superimpose the fluorescence microscope image of A viscosus on material A. So let's look at the number first. So for material A, there are more, we can see non-vital, which means dead cells. There are more dead cells than living cells. And then from the microscope image, from the fluorescence microscope image, we can see that on standard, also the green spots means living cells. And then the red spots means dead cells. Here we can see that on the standard, which is the control group, they have more living cells. And then, but on material A, which is the polybeads experimental group, there are more dead cells. We barely see any green spots in here. So which means that the antibacterial agents really works for this experiment. And another thing I want to talk, another problem with dental composite materials is polymerization shrinkage. So I talk about the concept of polymerization reaction. So it's after the lead curing process, the material is not gonna keep constant volume. There are 3 to 5% of shrinkage, and we really don't want it, because if there's shrinkage between the tooth surface and the filling material, it's gonna cause a marginal gap between these two surfaces, and it's gonna cause recurrent decay, because then the saliva or bacteria have the space to get in, and we really don't want it. This experiment, it was done in Turkey. It's trying to modify the composite material with zirconia. So what's zirconia? Here it shows a chemical formula of it. So in real life, we use zirconia to make man-made diamond. So it's almost as hard as that of natural diamond. And it can also reach the same clarity with natural diamond. And zirconia is also a very important material for dental crown. Some very dental crown, very hard dental crown, it has zirconia fillers zirconia in it. And they are trying to incorporate the zirconia into the dental filling materials to see how it would affect the polymerization shrinkage. I'm just gonna show the results very briefly. So this shows the weight percentage. 42, so they just, for this one, they put, there are 42% of zirconia material, and then the rest of them are inorganic glass fillers, which is silica. And then this one, they made 32% of zirconia fillers. Let's see this graph. So the x-axis is time, we see the days, and then y-axis is the volume changes. So we can see at the very beginning, we see the date in here, right? Oh, the dashed line, which means that they put it in air, and then this black line means that they put it in water. So the previous experiment, they immersed the material in real human saliva, but this one, they only immerse it in water and air. So this shows the air, and that's the water. So we can see the water group. We can see a dip here, right? So at the very beginning, there's a little bit of polymerization shrinkage, which is the dip in here. But after that, we see like it expands. So the material has some expandable properties, so which compensate for the polymerization and shrinkage. And their results shows that 42% zirconia are the best for this purpose, and it has almost 44% of reduction of polymerization shrinkage. So for dental composite material, I talk about the clinical issue like bacterial adherence and then the polymerization shrinkage. So these two are all the main cause of recurrent decay, and that's all. That's about it. Do you have any questions?
Question. When you talked about they were immersed in water, was the water held at a temperature that was?
Yeah, 40 degrees.
40 degrees?
Yeah.
Did they try that experiment in saliva?
Which one? This one?
one?
No.
Do you have any ideas about how it would impact the volume change?
I think it's just the property of the material itself combined with the glass inorganic filter.
If they did it in saliva, do you think the volume change would be bigger?
Oh no, it's not due to water solution. Yeah. They have, yeah.
Any other questions? Well, let's thank our speaker again.
Yeah.